as Jan told you yesterday, my first connection with Alexei is that I was a referee for his PhD thesis. And because I was convinced that he was a talented and promising young mathematician, I tried to convince him to join us at the École Normale Supérieure de Lyon. But he did not come. I think we could not compete with the atmosphere and the climate of Nice. And therefore, we could not initiate a collaboration at that time. Last but not least, I met you a long time later, maybe 15 years later, in a meeting in Porquerolles, and then we realized that we had something to do together. And it resulted in a few papers. I must confess that I know only a very small part of his work. I think it's we collaborated on a part which is not his main accomplishment. For instance, we could have collaborate on the George iterations, for instance, but we did not. Actually, I discovered the topic with another collaborator who is present here, Louis Sylvestre. So this is
Miss opportunity.
Yes, miss opportunity.
For
Yeah.
me.
For me too. So let's begin. I intend to speak mainly on mathematical gas dynamics, on Euler equations, even if what I discuss here has many applications. I shall tell you which one actually. So to fix the notations, y is the space variable, and it belongs to the whole space Rd. My problems are always Cauchy problems, pure Cauchy problems. That is, the domain is the entire space, and never a bounded domain, nor a periodic domain. I am really interested in Cauchy problem. T is the time variable. So mind that the space dimension is d. I shall use the letter n later on, which will be 1 plus d, the dimension of the time space. So the gas dynamics is modeled by conservation laws, that of mass, for instance, that of momentum, and conservation law or differential inequality, it depends on the model, for the energy. So here, rho is the mass density, u is the velocity field, sigma is the stress tensor, epsilon is the specific internal energy, and Q is the heat flux. Okay. So from this, you have the basic estimates that the total mass is conserved in time. I call it m, and the total energy is a non-increasing quantity. I shall always require this. So I have a notion of admissible solutions, and this notion includes essentially these two requirements, that the total mass is conserved and the energy is non-increasing. Non-increasing is not so much important. What I need is to have a bound of the energy uniformly in time, and let us call it E0. And in this work, the total mass on the energy bound will be finite. Let me denote ρ0, u0, and so on, the initial data of the Cauchy problem. You know that because the Euler equations or gas dynamics in general is invariant under change of observer, sigma is a symmetric tensor. The stress tensor is symmetric, and this is equivalent to saying that the angular momentum is conserved. So, for instance, in the Euler equation, the stress tensor is just the opposite of the pressure times the identity matrix, where the pressure, because we consider a compressible gas, the pressure is a non-negative function, which depends on both the mass density and the specific energy, the specific internal energy. But for the Navier-Stokes model, of course, the stress tensor involves the Jacobian matrix of the velocity. We can deal with other models, for instance, kinetic models. Here, this is the Boltzmann equation. I don't want to specify what is the interaction term Q of F. Just mind that the unknown is a kinetic density, a non-negative function, which depends not only on the time and the position, but also on the velocity of the particles. What is important is that the interaction term vanish when integrated against the first few momenta, and this implies after integration the conservation laws of mass, of momentum, and of energy. For instance, if you take the moment of order 0 and the moment of order 1, then they satisfy the conservation law, which is conservation of mass, from which again we have the conservation of a total mass, capital M, and so on. I can deal also with other kinetic models like mean field models, like Vlasov type. Here, the interaction term is replaced by this drift term, where F is a self-induced force. It can be a Coulomb force, for instance, a gravity, whatever. Okay. I shall not give details about Vlasov type equations, but I do have results also in this case. So the goal of this topic is to establish new natural estimates. And by natural estimate, I mean estimates which are given only in terms of the total mass and total energy, and possibly in terms of the moment of inertia at initial time. Mind that the moment of inertia is not a conserved quantity. It evolves in quite an explicit way, but it is different at different times. Now, these new estimates will look like Strickard's inequality, which means that they concern space-time integrals. For instance, that one. So this is the first new estimate that I got, in which you see that I involve only the total mass and energy, and I estimate some complicated, some not so complicated, but non-linear quantity, which involves the pressure and the density. But what is important is that it is a space-time integral. And also that this quantity is somehow of higher order than the usual quantity involved in conservation of mass and momentum. Here, the notation just means that there exists a constant CD, which depends only on the space dimension and not on the data, and for which the inequality is valid for every admissible flow. Okay. The tool that I use is, on the one hand, that the model can be written in this abstract form, divergence. So the divergence is both in space and time variables of a symmetric tensor, and this divergence equals 0. So what means the divergence of a tensor? It means that you just take the divergence, the ordinary divergence of each row of the tensor, and therefore you receive a vector of distributions, and you ask that this vector is identically 0. So, for instance, if you take the divergence of the first row, what you obtain is just the conservation of mass. And when you take the divergence of the other rows, then you have a conservation of momentum. So this is a way to rewrite the gas dynamics equations. Now, I want to apply a functional analysis result, which resembles somehow to Gallardo-Sobolev embedding. But it is not so simple. It is not so simple because if instead of the divergence here, I had an elliptic operator, then I could immediately get regularity results. And regularity results imply by Sobolev embeddings enhanced integrability. Okay? But here, the divergence operator, the row-wise divergence operator, is far from being an elliptic operator. Okay? When you consider the symbol consists just in multiplying the tensor by the frequency vector. And therefore, this product will be 0 each time the frequency vector is in the kernel of a tensor. And such frequency vectors, such non-zero frequency vectors will exist whenever the tensor is singular, whenever the determinant of a tensor is 0. And therefore, the characteristic cone associated with the divergence operator is just that of matrices whose determinant is 0. Here, of course, all the matrices are symmetric. Okay? So it is non-trivial, and the operator is not elliptic. Of course, you know that it is not elliptic. You already knew that because many systems, hyperbolic systems of conservation laws can be written that way, and they usually admit shock waves, discontinuities, and if they admit discontinuities, this means that there is no regularity, no strong regularity result. So you knew that, of course. However, the situation could be slightly better if you assume that the tensors are positive semi-definite. And this is because the characteristic cone here does not intersect the interior of the positive cone in the space of symmetric matrices. And therefore, there could be some compensation. And this is the topic I want to investigate here. Okay. So the name of the topic is compensated integrability, but what is it? So let me begin with a definition. So a symmetric tensor on a domain U is a domain in Rn, so it is an n by n symmetric matrix whose entries are distributions. Okay, so since they are distribution, I can define the row-wise divergence. I told you what it is. I just take the divergence of each row and I receive a vector of distributions. Now, if I assume that A is positive semi-definite, you know that a non-negative distribution is always a radon measure. So it's the same here. It's exactly the same argument. So when A is positive semi-definite, then certainly the entries are radon measures. And therefore, I shall say that a tensor is div BV if, on the one hand, the entries AJK are radon measure with finite total mass, as well as the coordinates of the divergence of a tensor. Now, I need another definition here. It is that of a normal trace. So let me assume that the domain has a Lipschitz boundary, and let me denote nu, the outer unit normal vector field, to the boundary. Then if A is div BV in the previous sense, then we may define a normal trace of a tensor, which is now vector valued, and it is defined by duality with the the usual definition. So it resembles very much the normal trace that you have when you study Navier-Stokes equation, for instance. Of course, this definition tells you only that the trace is a distribution on the boundary, a distribution of order possibly -1. Not worse, but possibly -1. Now, the following proposition can be used also to make a definition. But, okay, it tells you that if you have a divergence BV tensor, a diff BV tensor over the domain U, a bounded domain U, say, then the extension of the tensor by 0 outside of U, away from U, this extension is still diff BV over the whole space Rn, if and only if the normal trace is not only a bad distribution, but actually it is a measure over the boundary with finite total mass. And then the total mass of the divergence of the extension is just the sum of the total masses of the divergence inside U and the normal trace on the boundary. So let me now give you two elementary or not so elementary examples of divergence-free tensors. So divergence-free means, of course, divergence A equals 0. But they are illuminating for the theory. So the first one is that of diagonal tensors. Here I choose, I take U, the Cartesian product of intervals, and I choose functions fj, and each function depends only on n-1 variable, not n variable, but n-1. For instance, the j function does not depend on the j coordinate, which means that dj fj equals 0. And then I form the diagonal tensor with the functions fj. Of course, the divergence of the j line is just dj fj, it is 0. So this tensor is diff-free. And the theory will be, the forthcoming theory will be reminiscent to the Galliardo inequality, which tells you that the function defined as the product of the fj, which now is a function of all the coordinates of U, this function is integrable, and its L1 norm is bounded by the product of the n-1 norms of each fj. It is used at the beginning of Sobolev embedding course. The other important example, even maybe even more important, is that of special, I call them special tensors. Here I start from a function over the domain U, a scalar function, and I compute the Hessian matrix, 2 theta, and I take the matrix of its cofactors. The Hessian is symmetric, and therefore the cofactor matrix is symmetric. Now, if theta is convex, the Hessian is positive semi-definite, and so is the cofactor matrix. So everything is good there. But what is important is that this tensor is divergence-free. And this follows from Piola's identity, which is a classical identity used in particular in elasticity theory. Okay. Now, it turns out that if n equals 2, you have a converse implication, that is, every divergence-free tensor is special. This is quite elementary. But the converse is deadly false whenever n is bigger than 2, larger than or equal to 4. Now, I shall use this algebraic formula, which has nothing to do with differential analysis, of course. It's just a property of matrices. that the determinant of the cofactor is the determinant of the matrix to the n-1. Now, before entering in the theory, I want to convince that symmetric divergence-free or divergence-BV tensors are ubiquitous in mathematical physics. So I gave you a first example. It was Euler equation, or more generally, classical gas dynamics, even Navier-Stokes. Here is a second example. It is still gas dynamics, but in the relativistic context. So it is special relativity. There is a warning here in that the tensor will not involve the conservation of mass. Instead of using the conservation of mass, you must use the conservation of energy. Okay, so the first equation is the conservation of energy, and the second one, which is vector valued, is still the conservation of momentum. Okay, and this can be written as divergence A is 0, where A is the following energy momentum tensor. And okay, you can see that it is symmetric. This requires some explanation, of course. Why is it so? Why do we have so often symmetric divergence-free tensors in mathematical physics? And this comes from the variational principles that are at the core of mathematical physics. So many physical processes obey to a variational principle. So you have a Lagrangian with a Lagrangian L, with Lagrangian density straight L. It depends on a differential form alpha, which is closed. So d alpha is 0. I do not tell here. I do not tell you what is the degree of alpha. It depends on the kind of physics that you are considering. Okay? I shall give you examples. Now you want to write that variations of L vanish for every admissible variation of alpha. But what are admissible variations of alpha? Naively, we might think that admissible variations of alpha are of the form alpha epsilon equals alpha plus epsilon times some closed differential form, say a d beta, an exact differential form. Okay, this is the naive way. But if you do that, perhaps you will not get the right equations. For instance, if you do that for gas dynamics, you will get only the gas dynamics for irrotational flows. So you must not work that way. The way you must, yeah.
So at this level of generality, how do we interpret dx? Is that the metric volume form or a generic volume form?
Alpha?
Yeah. No. The volume, the integral over dx.
Okay. Dx? It's the space-time volume form.
So there's an implicit metric.
Yeah. Yes. Yeah. I think it could be even more general. But so the admissible variations are not that way. That is additive. They are instead compositional. That is, you consider any smooth flow. You take a smooth vector field, compactly supported, for instance. It generates a flow, which is a group of diffeomorphisms phi epsilon, and then you form the pullback of alpha, and for epsilon small, alpha epsilon is close to alpha. So these are the admissible variations. And when you do that, you receive, when you write the variational principle, you receive differential equations which govern the underlying physics. Now, it turns out that physics is invariant under the action of some group. So you have a symmetry group, G, and for every matrix in this symmetry group, the Lagrangian density is invariant. Okay? And This group may be formed of translations, rotations, or Lorentz transformation. It depends on the physics you are doing. Now, you know from Noether theorem that to every one parameter group of symmetry, a conservation law is associated. Okay, and for instance, if this one parameter group is the time shift invariance, then you get the conservation of energy. Space shift invariance yields conservation of momentum. And both these conservation laws gives you a divergence-free tensor. So say that you are in the physical space, dimension 1 plus 3, T is a 4 by 4 tensor, which is divergence-free. But it is not yet symmetric in general. Some ingredient is lacking here. And the fact is that the physics, the symmetry group of the model includes also rotations or Lorentz transformations. So that is, it contains the orthogonal group associated with a quadratic form. And here S is the matrix defining the quadratic form. And now, when you apply a Noether theorem to this, to the one parameter groups included in this orthogonal group, then what you find is that pre-multiplying this tensor T by the inverse of this matrix S, you obtain a tensor A. So pre-multiplying does not affect the divergence-free property. So A is still divergence-free, but now A is symmetric. So this is why you almost always have symmetric divergence-free tensor in mathematical physics. So I gave you two examples which were taken from gas dynamics. So in gas dynamics, for instance, in relativistic gas dynamics, a group of invariants is the Lorentz group. The differential form is of degree 3 in space-time of dimension 4. D alpha equals 0 expresses the conservation of mass. Now, my last example will be the Maxwell system in vacuum. And by Maxwell system, I do not mean the linear, the usual Maxwell system, but much more general systems for electromagnetism. Here, alpha is a 2 form, so the degree is not the same. Here it was 3, now it is 2. So, of course, E and B are the electric and magnetic field. Actually, it's only one field because it depends on the choice of coordinates. The closedness of alpha expresses the Gauss-Faraday law. And now, the divergence-free energy momentum tensor, which is provided by a theory, is given that way. So it is a bit ugly, but here, L is the Lagrangian density. E and B has been, are its arguments. And D and H are the gradients with respect to E and B. And they are called the electric and magnetic inductions. Now, it is unclear on this formula whether A is symmetric, but it is from Noether's theorem. And the symmetry amounts, for instance, to this cross product equals that one, and also this is symmetric. And these identities, you can check directly that they are equivalent to the fact that the Lagrangian density depends only on these two scalar quantities. And this is exactly the property of Lorentz invariance of the model. And this observation, I think, closes definitely the, what was called the Abraham-Minkowski controversy. At least in the case of the vacuum. The Abraham-Minkowski controversy was the following question. What is the energy flux in electromagnetism? And one of these people thought that the energy flux was this quantity, H cross E, and the other one thought that it was D cross B. And they fought very hard. Okay, two schools fought very hard against each other. And the answer is, but you have the same answer. Your choices are the same, actually. You should not fight. So let me go back now to the theory of compensated integrability. So remember that we deal with space div BV made of tensors that are finite measures, okay, whose row-wise divergence are finite measures. Of course, this mimics the space of BV functions if you replace tensors by functions, but there is a big difference in that the divergence operator is not elliptic, while the gradient operator is elliptic, of course. So for the BV space, you have this Galliardo-Nirenberg-Sobolev embedding with a corresponding functional inequality, of course. But we do not expect such a strong result for this BV. But in the spirit of compensated compactness, we expect that some nonlinear quantity, maybe, let us call it D of A, behaves better than the entries, that each of the entries Aij. But which quantity? This quantity, we shall guess it just by observing the two simple examples. So we could observe the diagonal case, for instance, the case of diagonal tensors, but the one which is more illuminating is that of spatial tensors, for which we have the following calculation. So here it is a calculation in the periodic case. So suppose that A is periodic according some lattice in Rn, so that the barred integrals are averages. So you can make this calculation. First of all, the n-1 root of the determinant of A is just the determinant of the Hessian of the potential. Remember, it is just a matrix property. It has nothing to do with differential calculus. Okay. Now, the determinant of the Hessian is clearly a null Lagrangian in John Ball's terminology, and therefore the mean value is the mean value of a Lagrangian. Null Lagrangian is the null Lagrangian of the mean value, something like that. And therefore, you have the following identity that this equals to the determinant of the mean value of the 2 theta, and then at the end you obtain this result. Okay, this suggests that the appropriate quantity D of A is the n-1 root of the determinant of A. This is the nice quantity. So let's see why it is nice. Okay, how it is nice. First of all, I want to emphasize that this quantity is a homogeneous function of A of degree n over n-1. So it is superlinear. Since it is superlinear, it is clearly not concave. But we know that, on the other hand, that the determinant to the 1 over n is concave on the cone of positive semi-definite symmetric matrices. And therefore, the determinant to the 1 over n seems to play an important role. And actually, it will. And we shall use it in order to study the determinant to the 1 over n-1. So here is the main reason. First, let me observe that with the exponent 1 over n, even when the entries are Radon measures, finite measures, then the determinant to the 1 over n is still a well-defined measure, just because this quantity is homogeneous of degree 1. Okay? And it is even absolutely continuous with respect to the trace of A because of the arithmetic geometric mean inequality. Okay. This is the geometric mean of the eigenvalues, and this is the arithmetic mean. So here is the main theorem from which all the other results follow. So let me consider a positive semi-definite diff-BV tensor over Rn over the whole space. Then the determinant to the 1 over n, which is a priori a well-defined measure, it is actually a function, an integrable function of exponent n over n minus 1. And there is a corresponding functional inequality. That is, you take the norm of determinant A to the 1 over n in this Lebesgue space, and you obtain this up to some exponent. Okay? So the corresponding inequality gives you an estimate of the determinant to the 1 over n minus 1 in terms of the total mass of the divergence of A. Of course, this inequality is homogeneous. And this result comes almost from free when you realize that the structure of divergence BV, the divergence BV structure for symmetric tensors is somehow dual to the Monge-Ampère equation, and more specifically to the second boundary value problem for the Monge-Ampère equation. So it seems strange that I have a boundary value problem here because my domain is Rn, but in the proof you make a truncation and you work on balls, for instance, of larger and larger radius. So it is in these balls that you apply Jan Brenier's result, Jan Brenier's theorem, which he got in optimal transport theory. So I shall not give you the proof, but I want to emphasize that in the functional inequality above, the constant Cn, so this constant, that one, it is explicit and it is sharp, actually, because the equality happens for some tensors, and more specifically for tensors that are the product of the characteristic function of a ball by the times the identity matrix. And for general domain, if you take a tensor which is the characteristic function of omega times the identity matrix, then what you receive is exactly the isoperimetric inequality. So you can see compensated integrability as some kind of extension of isoperimetric inequality, and also of Gallardo inequality and others. If A is the product of a scalar function times the identity matrix, then you recover the Sobolev embedding. Now, there is also a result in the periodic framework, actually. Now, let me assume that A is still positive and now periodic according to some lattice. Then, this is almost what I wrote in the previous slide, but we had the equality when A was the special tensor associated with a convex potential. Okay? Here, A is not special, and we only have the inequality. But you see that the inequality is sharp because it is an equality when A is special. Okay? And now this result does not follow from optimal transport theory. It follows from it is still a duality with the Monge-Ampère equation, but now I use an existence theorem in the periodic situation established by Jan Yan. Observe that if the exponent here was 1 over n, then this inequality should just be the Jensen inequality. associated with the fact that the determinant to the 1 over n is concave. But of course, it would not use any differential calculus. It would be true for any tensor and not only a divergence-free tensor. Let me emphasize that this theorem is only for divergence-free tensors. It does not apply to divergence BV tensor in general, contrary to the previous one. So this inequality can be viewed in the terminology of Fonseca and Muller, of the Philippis, as a divergence quasi-concavity, because it is mean value of a non-linear quantity is less than or equal to the non-linear quantity of the mean value under the condition that the argument is killed by some linear differential operator. Okay, and therefore you expect from this observation, you expect that there is a weak star upper semi-continuity result, and actually this is what we established with two of you, Luigi De Rosa and Riccardo Tione. So here is the result. You have now a sequence of tensors, which are this BV, such that their divergence is bounded in the space of measures, and the sequence converges weakly star in LP for some exponent P larger, strictly larger than n over n minus 1. Then up to a subsequence, the weak limit of the nonlinear quantity is less than or equal to the nonlinear quantity of the weak limit. Some extensions of this result were given by these people, but I think the most important improvement is that one made by my former colleagues in the case where P equals n over n minus 1, and there are very nice new phenomena of concentration in particular. Now, I have still about 15 minutes, I think. Okay. Variations on compensated integrability, I want to present two of them, which I use in the sequel. The first one is to observe that the determinant of symmetric matrices is very important in this talk, but the determinant is a homogeneous polynomial of degree n. And when you have an homogeneous polynomial, you can associate with it a multilinear symmetric form. For instance, if you have a homogeneous polynomial of degree 2 is a quadratic form, and you may consider its polar form. But you may do that whatever the degree of a polynomial. So for instance, there exists a unique n-linear form, which is symmetric in its arguments, defined on the Cartesian product of the space of symmetric matrices, such that on the diagonal, it coincides with a determinant polynomial. Okay, so this is elementary algebra. And now there is a nice trick, which was found by Lars Garding in the 50s. He remarked that a determinant is a hyperbolic polynomial. So Garding had a theory of hyperbolic polynomials, which are more or less symbols of hyperbolic differential operators. But hyperbolic polynomials have very, very nice algebraic properties. And in part, so hyperbolic polynomials have a forward cone, which correspond to the directions, the forward directions associated with the hyperbolic differential operator. And in the case of a determinant, this forward cone is just the cone of positive semi-definite matrices. And Garding proved that if all the arguments belong to the forward cone, then the n-linear form associated with the hyperbolic polynomial still takes only non-negative values. So for instance, here, the function dn, when applied to n tensors, a1, a2, an, taken in the positive cone, dn takes only positive values. Okay, so this is quite important in what follows. And for instance, I have the result that if I take now n div-bv tensors over Rn, which are positive, then, okay, this should be the determinant if all the tensors were equal to each other. I take the nth root, as usual, and as usual, this well-defined measure is actually a function integrable at the exponent n over n minus 1, so usual suspect. And we have still the analogous functional inequality. So it is strictly an extension of the previous theorem. Let me give you an application of this to functional analysis. It was known, for instance, that when you have a BV function and you make the convolution with the kernel 1 over R, then this BV function, then this convolution is a bounded, actually continuous function, and you have this functional inequality. A proof is that, first of all, BV not only embeds into L n over n minus 1, but actually in this Lorentz space. This was observed by Alvino. And on the other hand, the kernel 1 over R belongs to the dual of this Lorentz space. So this is the argument. But I shall give you an improvement of this result here. So in the previous theorem, let me choose A2 equals blah blah an equals a function f, a BV function f times the identity matrix. But A1 will be different. Okay, the truncation is not very much important. You have a function, compactly supported function, which equals 1 over a large ball, and then you let the radius go to plus infinity. That is not important. You have here a tensor, an explicit tensor, which turns out to be divergence-free. And now you have here an arbitrary function over the unit sphere. Okay? And you apply the previous theorem. And what you obtain is the following. This is almost the same as the Radon transform of a function f. So you take a base point z in Rn and a direction omega, an element of the unit sphere, and you integrate f along this line, z plus r omega, with a weight r to the n minus 2. If there was no weight, it would be a Radon transform. Then, for every BV function f, you have the following property that when you fix z as a function of omega, of the direction, this Radon transform belongs to this Lebesgue space over the unit sphere. And actually, this is uniform in Z. Now, since this Lebesgue space embeds into L1 because the unit sphere has finite volume, you can say also that the L1 norm is uniformly bounded. But this is exactly the classical inequality, that one. So this one is strictly better, actually. Now, the other variant, which is much useful for evolution problems, is the following. Now, I define n to be 1 plus d, and d is a space dimension. So n is the dimension of the time space, ambient time space. And I split the tensor accordingly. That is, rho is a scalar quantity, M is a vector, and this is a d by d tensor. And here, this is a definition for sigma. Sigma is this block minus this vector times itself divided by rho. Okay? And the sure complement formula tells you that the determinant of A is just rho times the determinant of sigma. And the positiveness of A amounts to that of rho and the sure complement sigma. Now, let me denote capital N the integral of rho in space, which is a conserved quantity because if A is divergence free, then you have something like the conservation of mass. And then you have the following result, the following estimate. We estimate always the same quantity, which is the space-time integral of the determinant of A to the 1 over n minus 1. Mind that 1 over n minus 1 is just 1 over d. And now this is estimated. So here I integrate in time only on the finite interval. So I have the d fruit of the total mass, and then the total mass of the momentum, m, at initial and finite time. Now, applications of compensated integrability. So it implies two models which involve positive divergence BV or divergence-free tensors. So this includes the compressible Euler, being classical or relativistic models. This applies to Boltzmann equation once you have averaged the equations to get the conservation of mass and momentum. This applies to particle dynamics, discrete particles dynamics, or to mean field models, so continuum particle dynamics, interacting particle dynamics, whenever the interaction force is radial and repulsive. And repulsive is the key condition which ensures that the corresponding divergence-free tensor is positive semi-definite. It applies to hard spheres dynamics also, and it applies to multi-dimensional scalar conservation laws. This is a work that we did with Luis Silvestre, who is in the audience. It does not apply when the tensor is indefinite or is not known to be semi-definite, okay? So for instance, it does not apply to Navier-Stokes because the tensor involves the gradient of the velocity, and the gradient of the velocity, you do not know whether it has positive properties. It does not apply to incompressible Euler equation because you do not know the sign of the pressure. It does not apply to the Maxwell's equations because it turns out that the determinant of the tensor is always negative. It is minus some square quantity. And above all, it does not apply to attractive particle dynamics. And here there is an important observation to make. Remember that the theory will result in Strickhardt-like inequalities. And Strickhardt-like inequalities, they are clearly in contradiction with concentration properties when concentration occurs for all times. If you have attractive particle dynamics, you expect that the particles will concentrate in some domain, for instance, think to a galaxy, okay, and forever, and therefore a space-time integral will be infinite in that case, because you have a non-zero limit as time goes to plus infinity. So, for instance, Euler system. So you have your favorite divergence-free tensor. The determinant is rho times p to the d. And the Cauchy-Schwarz inequality tells you that the momentum at each time, the L1 momentum, the total mass, if you prefer, the L1 momentum the L1 norm of the momentum can be estimated in terms of the total mass and the kinetic energy, which itself is bounded by the total mechanical energy. And therefore, the last theorem that I gave results directly in this inequality. I shall make some observation later, but we can improve it in the following way. There is an improvement which uses the observation that the projected group acts on the equations of gas dynamics. And it acts particularly well in the case of a monoatomic gas. So I shall give here you the result in this specific case, which corresponds to gamma equals 1 plus 2 over d for perfect gases. Which tells you that for full gas dynamics, P is 2 over d times rho and the specific internal energy, or in barotropic gas, P is rho to the 1 plus 2 over d. And now you have this estimate, which is an improvement of the previous one, in that here you have a time factor t. So this estimate is better than the previous one for large times. But now the estimate is in terms not on the energy, but the momentum of inertia at initial time. Now, in compensated integrability, everything is more flexible when n equals 2, which means here d equals 1. And this is why in one space dimension, you do get not only improved integrability, but also improved regularity. And this was done by my friend François Goltz, who got by related techniques that rho and u are in this Bezoff space in the monoatomic case. And he has also some other results for other gases. Now, these estimates are not the end of the story, because you may observe that, for instance, in this estimate, the left-hand side is Galilean invariant because it involves only internal variables, while the right-hand side is not. So what you can do is choose the best Galilean frame in which to write this estimate. And the best one gives you the following improvement, that you may replace the product of the mass times the energy by this sum. Here it is the mass times the internal energy, and here now you have this double integral, which vanishes, for instance, if the velocity is uniform. Okay, and the same thing in the second estimate. Now you may replace the product of the mass by the momentum of inertia by this double integral, which vanishes if the initial mass is concentrated in a point. Okay. Well, you remark that I did not use an equation of state, at least in the first estimate. But what it involves is only either a decay or a uniform bound of the total energy. Let me give you an interpretation. For instance, in the case where the gas is barotropic with an adiabatic exponent gamma, then when you write the conservation of mass, you are saying that rho is L infinity in time with values in L1 in space. When you write the conservation of energy, you get a bound of the internal energy, and the internal energy is proportional to the pressure, and therefore you write that the density is L infinity in time with values in L gamma in space. And now when you write the new estimate obtained by compensated integrability, you find that rho is in a Lebesgue space in both time and space variables with a higher exponent, gamma plus 1 over d. So you gain an exponent overall, but of course, to the price that now you have an integration in time. So in particular, this estimate tells you that the internal energy may not concentrate. So this, here I have a comparison. I think my time is over, no? Right, so, okay, I thought that 1 hour was a lot. So, so let me give you just this one also, which is in the spirit of what I did before. This is an estimate for the pressure. So here I define some kind of radon transform of the pressure. I have base points T on Z, tau on Z, and I integrate along a line with this weight, R to the D minus 1. And here I have a quantity which is related to the direction. And then this transformation gives you a function which, in terms of omega, is in LD over D minus 1 of the unit sphere, uniformly in the parameters, in the space-time parameters, tau on Z. So there are many new estimates of this type. And well, 1 hour is not long enough. Happy birthday, Alexis.